Alright, so we're going to talk about parametric equations for our conic sections. And really all this does is it relates our x value and our y value to a third variable, often called t, that allows us to graph things that are not functions. So our circles, a parabola that goes left and right, an ellipse, those are not functions, so x and y become a little bit difficult to graph them. So we put in this parametric parameter, often t, to do this, and we have something as we start to move through it called our t-step. So t is incremented by pi over 6, pi over 4, pi over 3, pi over 2. Those are the values that we're putting in, and we get values for x and y, and then we can plot those points just as you would. It looks like a Cartesian graph, but we have this third variable t that relates them. So this equation, x is cosine t, y is sine of t. We can see we have our starting point here. We get half of a circle. If we were to continue it, we'd fill our full circle. If we need to put something in a Cartesian form, we can start to solve for things using our identities for sine and cosine, and we can get something with just x and y if we need to. So here's another one where I have I have x and y related to each other in terms of t. I have some range on t, and I have some values that I need to put in, 0, pi over 4, pi over 2, 3, pi over 4, and I just fill out the table and see what happens. So I'm just trying to solve it. Again, you can use a calculator and get approximations, that's fine. We're going to look and see kind of what we have here as we move forward, and we have to be a little bit careful about how we interpret our pieces. So if we grab those easy values, right, there's some point that I have on my graph, 3, -4. I can see I start to get a smaller circle, so it's been shifted, and if we look about where that's gone, right, that 2 value has moved my x value over 2, -4 has moved that down 4, so my center has rotated. I still have a radius of 1 as we move forward here, because I haven't scaled sine and cosine by anything. So we've just moved the center of our graph by those values by adding those. Again, going back to our transformations on from before. If I need to put it into Cartesian form, then I need to use our identities. And the one we're going to use the most often is the Pythagorean identity. So I put first off everything to one side and just get cosine t by itself, sine t by itself, then square everything. And you can see then I can add those two together, because sine squared plus cosine squared is 1, and now we have our equation for our circle as we move forward. Alright, so this is another example. Again, as we're moving forward with our values, we can see how this general form starts to work, right? So I have my values here for our form here for a piece, and again we got our values within here. This is our general form. If this is my radius, if this is going to stay a circle, if these values are different, obviously I'm not going to get a circle as we move forward. So here's another example. Again, we make a table. We'll use our calculator a ton for this, and we can see that we're going to get an ellipse as we move forward with this. So we get our values, and again we're going to look mostly at the calculator, but we plot the points, like the ones that are easy. There's half an ellipse, and we can start to see things like our major and our minor axis. So in this case it was 2 out along cosine, so I had a minor axis of 2. It was 6 up, which makes me go 6 up, and that's going to be my major axis. So again, if we're trying to put it in terms of our Pythagorean identities, same process. We just take our values and use our Pythagorean identity and set them equal to each other. Again, if we take a general form and start to move this around, you can see that we'd have our pieces again. If we have a tangent and secant, which again they have ranges that are infinite if you think about their parent graphs, and so we start to get our hyperbolas as we do this. And so again, we fill out our table and we plot our points, and we can see that we would be able to solve for this. And as we move forward, we use our identities, not the Pythagorean, but we can solve these, and we find that we get our tangent values, right, and we can subtract them, and that's where our subtraction comes from as we move forward for the hyperbolas. So this piece here, deals with this identity, which comes from, again, the Pythagorean identity with some manipulation, and will lead us to a hyperbola.